Welcome to this video. My name is Phil and I am a senior lecturer in astrophysics at the University of Lincoln, and in this video I wanted to have a look at a particular method that is used to calculate the distance to a galaxy, and this is known as the surface brightness fluctuation, and it relates to kind of a smoothness of the galaxy which changes as a function of distance, and that property can then be used to calculate the distance to the galaxy. So galaxies are very large structures. They are made of billions and billions of stars, gas, dust as well, but mostly the stars we're interested in for this method because they're the ones really emitting the light, and they have a finite number of stars, and that then relates to how bright a galaxy is, or how bright this, or the surface brightness of a galaxy. More stars, more luminous stars, you're going to get a higher surface brightness for a galaxy. Now, the stars themselves also have a finite size, and at large distances, they're essentially going to be point sources of light. So we're not likely to really resolve individual stars in distant galaxies. If they're quite close, like Andromeda, we might be able to resolve some of those stars, but if they're quite a long way, then we're unlikely to resolve the individual stars. Now, if we have a look at a galaxy, just a single galaxy at the moment, then if you were to go in different parts of the galaxy, then you get a different amount of stars in each part. So if you look at the same kind of surface area in a galaxy, then the number of stars in that area as you move around changes. So you get a point-to-point variation in the number of stars there. And given the stars are the ones that are emitting the light, that's going to give you a point-to-point variation in the surface brightness. So yeah, you've basically got this sort of pattern, and you're going to have a point-to-point fluctuation in the brightness in this galaxy. This is then your surface brightness fluctuation. It kind of looks a bit like a pixelation then. So you've got groups of stars that are going to contribute to this. Maybe you've got a larger group of stars, which causes one of the brighter regions. Then there's less stars in the region next to it, and this is what's then your point-to-point fluctuation in brightness. Now also the stars in galaxies of a variety of different colours, luminosity sizes, so you get quite a wide range of luminosities from the stars in the galaxies. However, the surface brightness fluctuation as a technique treats it as an average luminosity then. It doesn't, you're not looking at individual stars. But there is some correction that you do if you know the population of stars in the galaxy. Now, at larger distances, so now let's say we take a galaxy, then we move it further away. If we look at the same kind of surface area that we would look at in a picture, like the actual area in an image that we've taken of it, but this galaxy is further away, we're going to end up with more stars in the same area of the image than we would do if it was closer. So what does that actually do? Well, it kind of makes the galaxy appear smoother. You don't get the really sharp resolution as if it was closer. So galaxies that are further away appear smoother. So that surface brightness fluctuation, the point-to-point fluctuation, decreases the further away you go because you've got more stars being grouped together, and the fluctuations are beginning to be smoothed out essentially. So the way this technique can be used is that if a galaxy is twice as far away from another one, it will appear twice as smooth. And then another one that is 4 times the distance is going to appear 4 times smoother. So if you can work out the smoothness of the surface brightness, then you can then work out the distance to it as well. So it's a technique that can then get you your distance. It does kind of have a bit of a upper limit to how far you can calculate a distance. It's generally typical or useful to around about 100 megaparsecs. There's a galaxy here, IC 485, which is kind of around about that upper limit. And the problem what happens is you can't resolve any fluctuations beyond this sort of point. So they become kind of too small, and too small for the pixels you get on the image, so you don't really get any point-to-point fluctuations. It's very hot. Basically, the technique doesn't really work very well when they get too far, is the point. And probably an example here is another galaxy, which is one of the furthest away galaxies we've ever found, which is GNZ11, about 4 billion parsecs away. And you wouldn't be able to use the technique here. It's too faint, and you've not got a really good image of it anyway. because you just don't get the fluctuations then. So it's not a viable technique for the most distant galaxies. It's better for kind of mid-range, those sort of galaxies really. Now, they will also be calibrated with Cepheid variable stars. So you can independently get a distance to the galaxy using Cepheid variable stars, which are pulsating stars, and they have a regular pulsation period which relates to how bright they actually are. So if we can measure the brightness of a star as it gets brighter and dimmer, we can work out how long it takes to do that cycle. Now, if we know what the relationship is, then we can work out its absolute magnitude. So if we were to measure a period, we would then go to the relationship on this graph, and we would cross-reference it with an absolute brightness or absolute magnitude that star has. We would measure the apparent magnitude, and then we can use this equation to get a distance in parsecs. So it will be independently verified or calibrated using Cepheid variable stars to actually use as a surface brightness fluctuation method as well. Now, it kind of works quite well for the older elliptical galaxies. So these are more elliptical shaped galaxies. They don't have the spiral arms. They are not disc-like, so they're kind of they're more spherical shaped or ellipsoid in shape. These have a more consistent stellar population. So from one elliptical galaxy to the next, their stellar populations are more comparable or less similar to one another. And because of that, they behave more like a standard candle. So you basically, it's just easier to use these essentially than a spiral galaxy, which may have larger variations in their stellar population. But either way, you're probably going to have to do some correction for the age and the metallicity of the stars that are in the galaxy. So you would measure the population of stars in a galaxy, how old they are, their metallicity, things like that, their luminosities, and then you would do some correction for that so that each galaxy can be kind of comparable, and then we can then calculate a distance to it. So thank you for watching, and if you enjoy, then do check out some of the other videos.